So this is static equilibrium and elasticity. Hold on, we did equilibrium before. Elasticity is tacked on. They needed somewhere to put it. It's only a small section, so they just said, well, shove it at the back of this thing. This is basically a section where we're going to do some skills. It's basically going back a bit like doing Newton's second law and all that kind of stuff. We're going to talk about center of gravity. I'd forgotten that bit. We're going to talk about static equilibrium. We're going to talk about elastic properties of solids. So 3 little bits. Yeah, okay. So basically, things tend to rotate about their center of mass. Yeah, okay. So we need to be able to find our center of mass. We've done that. And then big things tend to rotate about their center of gravity. And that can be a weird situation where we have, say, 2 planets that are two galaxies that are interacting. Or if I had a really, really long rod which went from here 5 Earth radii into space. Its center of mass would be its middle, because it's the center of all the mass. But because one end of that rod is close to the Earth and the other end of that rod is way in space, the pull of gravity is different from one end to the other. And so we have a very different center of all the weight, if you like. So we need to be able to distinguish between these 2 things. And as always, when they're similar but different, you've got to put them side by side and compare and contrast. So center of mass is the point, and we do it in 1 dimension, so we need to find a pen. So we do it in 1 dimension, and we say, okay, it's going to be, the point at the middle of all the mass. And we say, well, if we have a series of discrete particles, then what I can do is I can say, what's the mass of this first one, and how far it is away from my starting point? What's the mass of the second one, and how far is it away from my starting point? And then I can say, so what I do is I say, it's the sum for each mass of the mass times the distance to the starting point divided by the sum of all the masses. We did that before, yes? So what happens because of weight? Well, because of weight, if you imagine it, we kind of got this thing where the bit that's near the planet has a lot more weight for a given amount of mass than the bit that's far away from the planet. Yeah, it weighs more down here. That 1 kilogram of matter weighs more down here. It weighs 10 newtons. Whereas if I go, 5 Earth radii out, that 1 kilogram probably only weighs about, 6 newtons. So it's no longer equivalent. What we find is that if my center of mass is there, my center of gravity will actually be more towards the one side than the other. Yep. We've got to figure that out. How do we figure that out? Well, we say for a discrete set of masses, then take each mass and find its weight and multiply each weight by that position and then divide it by the total weight. So, it's how do you pass this? I could just as easily go x center of gravity equals the sum of the weight of the first one times xi over the total weight. And that's saying the same as that in just different terminology, because how do you find the weight? Oh, weight equals mg. So it depends how you want to, I don't learn 2 different equations. I know how to go from mass to weight or weight to mass, so I just do the conversion. So, okay. 2 kilogram particle is located at +3 on the x-axis, and a 6 kilogram particle is located at +8. So we're starting off with the origin, and we have a 2 kilogram particle, and this is at +3 meters. And then we have a 6 kilogram particle, and that is located at 8 meters, +8 meters. And the gravitational field strength, interesting. the gravitational field strength minus 12 over x. Where on the x-axis is the center of mass. I don't need this for the, I don't need that bit for the center of mass. I go x center of mass is equal to the sum of each mass times its position over the sum of the masses. Let's put some numbers in. So x center of mass is equal to, well, this is going to be, pick the first one.
If you just use one sum sign, would that be the same thing?
If I just use one sum sign.
Yeah, like to the left. And just do mi xi over mi, that's still the
If you did mi/xi over m,
No, like,
that's not the same.
no, I mean like...
If you did that,
Yeah, that's what I mean.
I suppose you got eyes in there, so you're distinguishing between them, but no, it's actually not the same. That's not the same, because this cancels to just xi.
Oh, okay.
Yeah, so it's not the same. Okay. So then I say, well, this is 2 times 3 plus, that's going to be 6 times 8 added 2, that's going to be 2 plus 6. So this is going to be 6 added to 6 eighths of 48 over 8. So that's going to be 48, 54. 54 over 8, which equals 6 eighths of 48, 6.75. And the units will be in meters because we're measuring a distance. So did I do that right? Let me just check it with my glasses on. So that's going to be 6, 2 times 3 and 6 times 8, and then 2 times 6, 2 and 8. Yeah, I did 2 and 6 added together. So I think that's right. Okay. So let's see what this would happen now if we had a gravitational pull. Now, the gravitational pull. So we're going to do a weight. Okay. The gravitational pull is minus 12 over x, where x is the position. So this first one is minus 12 over 3, and the second one is minus 12 over 8. So actually this first one is a bigger pull than this second one. So just to get a scale for these things, this 2 kilogram proportionately weighs more. I don't know whether it does or not, because it's not 6 kilograms, it's only 2. But the pull of gravity on this 2 kilogram is bigger than the pull of gravity on the 8 kilogram. Agreed? So then I'm going to say, well, my x center of gravity, and I'm going to practice my new thing that I just decided. I'm going to do weight I xi over the sum of the weight, just so that I can...
So the W's in the stand for weight?
That's what I just made up, yeah. And this equals the sum of migi xi over the sum of migi. And let's pick our first mass. So it's going to be 2 kilograms. And the gi is going to be, if I look at my expression, minus 12 over 3, because it's at position 3, times position 3, 3 meters, plus. So you see where that came from? I took the mass, and then I substituted 3 in for x on this expression up here. So I got minus 12 over 3, because its position is at plus 3. And then I multiplied by its position, because that's what it tells me to do. And then I look at the next one, and the next one is going to be, what is the next one? The next one is going to be 6. And then my pull of gravity is 12 over 8, minus 12 over 8, of course, times my position, which is 8. So that's that one done. And then I've got to add together these two weights. So it's going to be 2 times minus 12 over 3 added to, that's going to be 6 times minus 12 over 8. So x centre of gravity is equal to, let's have a look, that can cancel, so that would be minus 24. Minus 24. Those two cancel. That's going to be added to. That's going to be minus 72, sorry. Over. And then I look down here, and they don't cancel, so that's minus 24 over 3 is 8. Added 2. And then we have 6 12s are 72. 72 over 8 is 9. That's minus 9. Yeah? So that equals minus 24 minus 72 is minus 96 over minus 8 minus 9 is minus 17. So I'm going to get a positive number, but I have no idea what it is. Let's get my calculator. So I'm going to get 96 divided by 17 equals 5.6. It's in meters, it's position, yeah. So let's look at this on our diagram. Let's just change my color of pen so I can show this. So if I look at this, my center of gravity, sorry, center of mass, I'm sorry, was at 6.7, so it's kind of like there. There's my center of mass. And my center of gravity is at 5.6. And that's because there's more gravity at this end than there is at that end. Now, how can I physically make this occur? I can make this occur by having a planet over here. So here's my planet causing this gravity, and it pulls on this moon, even though it's small, with a greater gravitational field than it pulls on that moon. That's the realistic calculations you have to do when you're dealing with center of gravity. Okay? Okay? So know the two equations and just know how to do it. So draw a line, static equilibrium. We did equilibrium. We know the sum of the forces along any line equals 0. That's equilibrium. That was good old Newton's first or second law? First law. Sometimes called the law of inertia. Okay. So who needs this? Let me give you an example. You have a big log, and I want the log, so I'm pulling in that direction, and you want the log, so you're pulling in that direction, and we're both as strong as each other, so we have stalemate. That's equilibrium, isn't it? It's not that nobody's pulling, it's that we're pulling to the same extent in opposite directions. Agreed? But let's say, I'm going to just draw it next to it. Let's say that we've got the same intent, but we don't line up well. I pull there, and you pull here. That's not in equilibrium. It is from a force point of view, but from a torque point of view, no, this thing is going to start turning. So true equilibrium, which involves no acceleration anywhere, but also no turning acceleration, I need to take into account the turning effect. So I've got to take into account torques. So you remember the first condition for equilibrium, that the sum of the forces equals 0? Well, now we have A second condition for equilibrium, which is the sum of the torques about an axis, must equal 0. And just like with the forces, we were careful about what line we resolve things along. So we're going to be very careful about what axis we resolve things around. We resolve torques around. You can pick a nice one and life gets easy. You pick a bad one and life gets complicated. So strategic thinking becomes important. The location of the axis does not matter because, so in terms of equilibrium, the location of the matter does not matter because for an object, if an object is in rotational equilibrium about one axis, it's in rotational equilibrium about all axes. But mathematically, it matters a lot because just because it means it's in equilibrium doesn't mean to say it's easy to work out. But if it's not that this object is in rotational equilibrium about that axis, but it's not about that axis. They're parallel to each other, so they're going to be in rotational equilibrium about both. But which one you pick to work out using your problem matters a lot. If two forces are acting on an object, so here's one force acting at D1 and here's F2 acting at D2, then this one creates a counterclockwise torque and this one creates a clockwise torque. So we'd call this one positive and this one negative. Just like we had the positive end of the line and the negative end of the line, we need to have a positive torque and a negative torque. And so we decided to make counterclockwise positive. There's 4 classic examples of this. There's more, but there's 4 classic ones that we have. Let's have a look. We have the seesaw or the teeter-totter, the balanced beam, and then we have the boom and sheet if you're a sailor, or the plank and the string if you're not, or the mast and the plank and the whatever you like. And then we have the ladder leaning against the wall. And these are these classic physics situations that every engineer's done. Because later on, you're going to go to your university of choice and you're going to be doing statics as an entire course. Imagine an entire course of this, okay? And I'm going to get to that in a minute. We are going to do an entire course of this. And you're going to do about trusses. And trusses are like those sections of bridge or those sections of a railroad truss where it's basically got a whole bunch of popsicle sticks with gaps in between, but it's really strong. So rather than in your ceiling of your house, there will be a truss holding the roof up, and it's a mechanical structure which has the minimum amount of weight for the maximum amount of strength, really. When just by the by, when I did Physics 1, we had to make a beam. This was the first thing we made. We had I remember it to this day. We had a connection here and a connection there, and there was a load here at so many meters away, and we had to make a truss such that it could withstand a certain load at that position. And the rest was up to us. And so it was great. We had welding machines. It was like I always wanted to weld something. And we had welding machines. And some people, did, complicated designs. And some people did simple designs and so on and so forth. And there was more than one way to solve this problem. And you got charged, not literally, but in an imagination, we got charged for every spot weld. You want to go in?
Have a budget?
So basically, it was a performance cost ratio. And basically, so if you could reduce the number of spot welds, that was better. If you could reduce the length of, you got this whole length of steel, and you could cut it up as you like. So if you could reduce how much of it you used, you saved money. And then we tested them. And mine was a very mediocre design, straight out of the textbook. Very, very mediocre performance. And but I passed.
So these are like balconies hanging off of?
It'd be that kind of thing, yeah. And then later on, we did an actual beam, a 3-dimensional beam, where again it had to fasten here and fasten there. Sorry, it had to fasten there and fasten there, and there had to be a load here, and it had to various things. Now this is 3-dimensional now, so it's got a square cross section, and we're in teams for that. Me and my buddy. Neither one of us wanted to be an engineer. We didn't think we wanted to be engineers, and so we did it, and my performance was terrible. In fact, we sent it in to be tested, and the professor looked at it and said, I don't want to be mean-spirited, but you're not going to pass with this. And I said, why not? And he said, well, you know how books of matches, when you take the little tray out from the book of match, it just collapses. You know, if you have just a thing like that with nothing inside it, it just collapses. Because you don't have bulkheads. That's a bulkhead. He said, no bulkheads, it won't survive anything. So he said to us, I'm going to turn this off because you...